Welcome to geometry class. Today we'll talk about situations in which we're trying to prove that a particular quadrilateral is in fact a parallelogram. In a prior lesson we looked at quadrilaterals that we knew were parallelograms and we drew a bunch of conclusions about those parallelograms. In this lesson we're looking at quadrilaterals that we don't know whether they're parallelograms, and we're trying to figure that out. We're trying to answer the question, is this a parallelogram? There's a number of theorems that we'll look at, and most of those theorems relate to or are the converses of theorems we learned in a prior lesson. So let's look at those. The first one is called the converse of the parallelograms diagonals theorem. We already looked at parallelograms diagonals theorem. This is the converse. It says if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Just take a look at that and prove it real quick. Notice when we see this diagram, we don't know that it's a parallelogram initially. All we know is it's a quadrilateral. It has the diagonals drawn in, and the diagonals bisect each other. The question we're trying to answer is it a parallelogram? And the converse of parallelograms diagonals theorem does in fact answer that question. Let's just prove it real quick. Right here I've got a situation in which I have smaller triangles. I'll just outline those real quick. I've got a triangle here and a triangle here. I'd like to just draw your attention to those. And we notice that these two sides are congruent. And these two sides are congruent. We could ask the question, are those two triangles congruent? The answer to the question is yes, they are. And just to sort of figure out why we know that, it's because we have here vertical angles. So by side, angle, side, we have congruent triangle. If those triangles are congruent, by CP/CTC, this angle congruent to this angle. And we can see here, when we look at this line over here on the right side and this line on the left, and this diagonal as a transversal, by the converse of the alternate interior angle theorem, we know these lines must be parallel. We can then shift our attention to this triangle and this triangle. And again, we can sort of run the same game here. We know that by side angle side, that is side angle theorem side, those two triangles are congruent. Since those two triangles are congruent, corresponding angles in those two triangles are congruent, such as those ones. And since those two angles are congruent, we know we have a line here, and a transversal here. And again, by the alternate interior angles theorem, we can conclude that these two sides are congruent. Once we do that, once we conclude that those two sides are parallel, we have here, by definition, a parallelogram. You can see that we have two pairs of parallel sides, and that is the very definition of a parallelogram. So we prove here that anytime we're dealing with diagonals that bisect each other in a quadrilateral, that we are in fact dealing with a parallelogram. How do we actually apply this rule? We might have a situation that starts like this. Maybe this is 10. We'll call this AB. We'll call this down here CD. And we're asked to find the length of segment CD. The answer is 10. Now, let me just stop here for a moment and say something. It'd be tempting to just jump to that conclusion as soon as your eyes hit this thing. It kind of looks like a parallelogram, then it must be a parallelogram, right? No, wrong. We need to be able to prove first that it's a parallelogram before we can go ahead and apply the rules that only work inside parallelograms. So here, I'm looking at the diagram. I don't yet know that ABCD is a parallelogram, but as soon as I see that these diagonals bisect each other, then I conclude by the converse of the parallelograms diagonals theorem, just to put a name on it, that it is in fact a parallelogram. And once I do that, I conclude by the parallelograms opposite sides theorem that AB and DC must be equal. So there's a process involved here. Right now in this lesson, we're just trying to establish that these are parallelograms. Once we establish they're parallelograms, then we apply all the rules that we looked at in the prior lesson. Look at the next rule, quadrilateral opposite and parallel sides theorem. Again, this is the most cumbersome name I could possibly think of. I did that to torture you. You may think of an easier name. I don't know. Maybe you don't even want to think of the fact that it has a name. It doesn't matter as long as we know that the rule exists. It says if one pair of opposite sides of a quadrilateral is both congruent and parallel, then the quadrilateral is a parallelogram. Here's a quadrilateral. It has four sides clearly. We can see that there's one pair of sides that are both congruent and parallel. And we'd like to try and figure out whether we can prove that this is in fact a parallelogram. As we look at it, I'm not so sure. I don't know. Can we prove that it's a parallelogram? The answer is yes. The way that we do that, let's begin by drawing in this diagonal here. When we draw in the diagonal, we can see we have parallel lines. We have a transversal. We know by the alternate interior angles theorem that these two angles are congruent. We know by the reflexive property that this side is congruent to itself. So I think you can see we have side, angle, side. And by side, angle, side, these two triangles are congruent. All right, where does that get us? Well, it allows us to conclude that these angles are congruent because they're corresponding angles. If those corresponding angles are congruent, then we can see this as being two lines with a transversal. And in that context, these are alternate interior angles, and therefore the converse of the alternate interior angles theorem tells us that these lines must be parallel. All right, where does that get us? Well, I think you can see we end up arriving at a place where we're looking at the very definition of a parallelogram, two pairs of parallel sides. Let's look at the next rule. Converse of the parallelogram sides theorem says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Let's see if we can prove that. Here we have a shape. We don't know what shape it is exactly, but we can be sure that it's a quadrilateral because it has four sides. In this case, we can just draw in a diagonal. I think you can see by side, 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 these two triangles are congruent. If the triangles are congruent, then we can apply CP/CTC. Once we apply CP/CTC, we can look at the converse of the alternate interior angles theorem to conclude that these are parallel. We can also look at these two angles as being congruent by CP/CTC. And once we do that, we can conclude, again, by the converse of the alternate interior angles theorem, that these lines are parallel as well. And what do we end up with? We end up with a situation in which we have two pairs of parallel sides, and by definition, that's a parallelogram. One more rule to look at. The converse of the parallelogram opposite angles theorem. It says if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Let's look at this. This one's a little trickier to prove. We need to be a little more careful. If we draw in the diagonal here, such as this one here, draw in the diagonal, we've really destroyed, so to speak, some of our information because we just cut those angles and we don't really know how we cut them. In other words, just because I cut two angles doesn't mean that I know I've cut them the same way. So I cannot be sure that any sort of congruent statement applies with these newly formed angles. So that's not going to work for us. Instead, what we're going to do is we're going to take a slightly different route. I'll just label these vertices so we can talk about them, A, B, C, D. And notice, because this is a quadrilateral, the sum of the interior angles is some fixed number. We've already looked at that in a prior lesson. We know that the sum of the measures of all of these angles, angle A, B, C, and D, is equal to n minus 2 times 180. Therefore, in this case, since this is a quadrilateral, we know it's 4 minus 2 times 180, which is the same as 2 times 180, which is, of course, 360. So if we add up A, B, C, and D, though, the measures of those angles, we'll end up with a value of 360. What we can do now is assign these angles variables. I'll say this is x degrees. Now this one is probably different, that is, B is probably different than A. So I'll call that y degrees. When I come down to C, I can say that that's also x degrees because it has the same measure as A. They're congruent. And likewise with D, we'll say that that's y degrees. So as we go to sort of write out this equation, I end up saying that x plus y equals 360. Now, as I continue to simplify this a little further, we can see that it's 2x plus 2y equals 360. And therefore, 2 times x plus y, I'm just factoring those two terms out, is equal to 360. Finally, if we divide both sides by 2, we can see that x plus y equals 180. Okay, so now we know that x plus y is equal to 180. That means they're supplementary. And we have a rule that is called the converse of the same side interior angles theorem that says if we have a transversal and we have two lines, such as these two here, x plus y equals 180. So these are supplements. The converse to the same side interior angles theorem says if we have two lines and a transversal and same side interior angles are supplementary, then what? Then the sides or the lines are parallel. We can apply that exact same rule here in this context, looking from a different perspective. Again, we have two same-side interior angles. We know that's supplementary, and therefore these lines must be parallel as well. And that leaves us with a shape that we know is a parallelogram by definition. Two pairs of parallel sides. So that's the proof of the converse of the parallelogram opposite angle theorem. All of these rules that we looked at today in this lesson, all they do is allow us to look at a quadrilateral and answer the question, is it a parallelogram? Work through a few of the example problems. Make sure you have a good idea of how to apply them. If you have any questions, please send me an email.